Thank you so much, Phyllis. So with this, super happy to introduce the team in charge of building our capacity in AI and machine learning. But most importantly, they will tell us how we can adapt this approach to food environment monitoring to the African context. So Hala and colleagues, please you have the floor.
Thank you so much, Silver. I'm just going to share my screen. Thank you so much. So thanks very much. We're really pleased to be here. Thank you for the invitation to share some of what we've learned. I'm not sure we're experts from applying machine learning in food environment research. And really, we'd like to engage in discussions with you about considerations for adaptations in the African context. Today, my colleagues Shadil Bassiouni, Christelle Ael, and I will be presenting this work on behalf of a team of researchers from the American University of Beirut and the Tunisian National Institute for Nutrition and Food Technology. And the project from which these data derive was generously funded by IDRC Canada. So during this workshop, I'll be giving you some background on our study entitled School and Community Drivers of Child Diets. And then Shadi and Christelle will talk about some of the methods we used to generate data on food environments and then to classify food exposures within environments using machine learning. And they'll be talking about two different data capture methods as well as classifying using machine learning. And then we'll try to extract some lessons learned from our experiences for potential use of similar methods in the African context. But before we start, and in the hope of making this workshop as interactive as Zoom will allow us to, we'd love to hear from participants here about how you think machine learning can be useful for the kind of research you do or plan to do, or if you already have experience in using machine learning in food environment research. So I will ask you to either scan the barcode on your screen or go to menti.com and enter the code 17932525, and then tell us in a few words, so it's an open box, what you're thinking when you consider the use of machine learning in your research, any thoughts of what you think the potential of machine learning can be for you. So it would be great if you could let us know so that we can also hopefully respond to some of your interests during this workshop.
I was just wondering if we could have the link to Menti in the chat box.
Sure. Maybe Christelle, you can add it.
Right, I think it's already in the link. And the code, if I'm right, is 17932525.
17932525. And if you're on your phones, you can scan the QR code and hopefully we'll start to see your responses. So for complex statistical analysis, for transcription in qualitative interviews, supporting document screening in systematic reviews, supporting data extraction, prediction models for food security, consumption, tagging and organizing images to simplify coding. Doing this manually takes so long. Yes. Identify channels of food waste. Great. Anyone else want to chime in before we move forward? Synthesizing results. Yeah. So conducting an inventory of unhealthy foods on the market. So from our perspective, we're very much going to be talking about a couple of these in that we're really going to be focusing on tagging, organizing, coding, largely image-based data. But a lot of the methods that Shadi will be describing and the approaches to training data and then using this kind of data for machine learning can be applied in many of the other aspects that you were interested in. So we will move on. So I'll talk a little bit about our case example of applying machine learning in the SCALE study, which was conducted in urban settings in two middle-income countries. So Beirut in Lebanon, in the Middle East, and Tunis in Tunisia in North Africa, which have both been going through rapid nutrition transitions. And also just to frame our study, we focused on children aged 9 to 12 years of age and considered that for this age group, when we talk about food environments, we're really looking at school and neighborhood food environments that would be important intermediate structures that could influence children's food choices and their diets. So the scale study aimed to identify factors that influence children's food choices and diets within those neighborhoods, school and neighborhood food environments. And we set out to develop what we term sort of context-specific methods that would allow us to describe these environments in these contexts. If you want more information on the larger study, this QR code can lead you to our website. But for today, although the study accounted for factors at macro, meso, and micro level, what we're going to zoom in on today is the meso level environment within which children are exposed to food or food cues. And for us, the first part of that environment we refer to as the wider food neighborhood, which really consists of exposures to food or food cues in children's daily trajectory. And for us, the way children's daily trajectories were conceptualized was a typical school day and children's routes to and from school. And then the second part of that environment was the school neighborhood environment, which really considered proximity, density, and typology of food outlets and food advertising around schools. So these are the components of food environments that we're going to be discussing today. And I just want to briefly highlight that for the purposes of our study, the methods we used to capture data on these food environments really relied on images that we collected either passively using wearable cameras or actively through ground truthing and geospatial mapping. And really the application of machine learning that we're going to be describing today and that we use largely relies on the detection of objects in images and their classification, or what Shadi likes to refer to and computer scientists like to refer to as computer vision. And so in our case, this was used to identify faces and blur them, to identify food-related objects in children's environments, and then attempt to classify food and non-food items, and then make sense of the food items that were being detected. So Shadi, who is our machine learning expert, is now going to take us through the development of some of these protocols and some of the results derived, more specifically focusing on data from our Tunisian study. So Shadi, the floor is yours.
Right, thank you, Hala. Perhaps we can go to the next slide. Yes, so as Hala was just saying, one of the things for which we used machine learning and particularly computer vision is to try to map children's trajectories from home to school and the other way around to capture their food exposure. And by food exposure, we mean everything that children see that is related to food in their close environment, so actual food, but also food outlets and food advertisements. And this is extremely difficult to accurately capture through traditional surveying techniques, particularly if you're working with children. Okay, next slide, please. And so we really needed to rely on technology or innovative tools such as machine learning to be able to do this. If you look at the literature out there, there are very few studies that attempt to do something like this. So basically using machine learning in food exposure detection. And most of these studies really focused on ads, outlets, and menus. Since these are easy, I mean, it's easy to classify food items in those, either based on their brands or known ingredients. And most of these studies also relied on publicly available data sets, and most of them focused on high-income countries where our user studies really were going to take place in middle, low-income countries. So really, we weren't able to use anything that is out there to achieve our goal. So we had to build our own tool to capture children food exposure. And to do this, we designed a culturally acceptable machine learning-based tool that is going to capture children food exposure on their daily trajectories to and from school. And the design of this tool was guided by a user-centered design study, which included 12 workshops, 4 in Lebanese schools and 8 in Tunisian schools, since our user studies take place in these 2 countries. And these workshops included 6 with children and 6 with their parents and school staff. And they were very interactive workshops using storyboards and discussion with the participants in order to see how they envision this tool and what they require in such a tool to be so that they could use it. And this is a summary of some of our findings or results from the user-centered design study, which really highlights the characteristics that the children and their parents required in such a tool that we're planning to develop. So, for example, one of the big concerns was privacy, and they suggested, for instance, using face blurring to ensure that people that are appearing in those images, their identities are protected. Additionally, they also preferred, for instance, passive data capture through wearable cameras. Thank you. So this is exactly what I'm going to focus on right now. So I'm going to talk about this passive data capture approach through wearable cameras. Our protocol, data collection protocol, that was inspired by the findings from the user-centered design study works as follows. So we're going to use wearable cameras that continuously record videos of the child's environment for 24 hours. And these cameras must be password protected and with no internet access or removable SD card to ensure that in case of loss or if the camera is stolen, that the data is protected and nobody has access to it. They also should be shock resistant and firmly attached to the child so that they do not obscure them while they're doing activities. And of course, they can be turned on and off at any time, again, to preserve the privacy of the children participating in the studies. And once this continuous footage is collected, a machine learning model will be employed that is going to extract images from the footage that is related to food and discard anything else. And then for the retained images that have something to do with food, all the faces in those images will be blurred. And then finally, a screening phase by the parents will take place to allow the parents to actually even remove further images that they do not want to share with us as researchers. Before I dwell into how we built this machine learning model and the other components of the tool, maybe I will just brief you about the requirements for any machine learning project. So typically, one of the first requirements is to define the task. So what do you want this machine learning model to achieve or perform? And that's typically defined through defining what is the input of the model and what is the output. In our example, for instance, we wanted the machine learning model to take as input an image and decide whether this image has anything to do with food or not. The second step, once we've defined the task, is to actually build a data set that we could use to train this machine learning model so that it can automatically perform the task on real data. Typically, this data set has to be representative of the cases that we will encounter in reality, has to be sufficiently large to cover all those cases. So for instance, in our case scenario, we wanted to differentiate between images that contain food or have anything to do with food and images that don't. And so our data set would have to contain sample examples of images that have something to do with food. And remember that we do not want to capture only things that have to do with food items, but also advertisements and outlets. So it really has to have all of these examples. And then for the other class, we need, things that are would encounter in reality, so the children would see in their daily trajectory, but have nothing to do with food. Thank you, Hala. Okay, and finally, this is the machine learning workflow. So once we have the data set, it's typical to split it into two parts: the training data, which is used by a machine learning expert to train a machine learning model. And then this model is applied on a subset of the data set, typically called the test data, which I refer to as the input data here. And this test data is used to evaluate the model using standard metrics like precision, recall, accuracy, and F measure. And based on the results of the evaluation, either the model has to be tuned through adjusting the training data or adjusting the model, or until we're satisfied with the performance of the model, and then we can deploy it in real user studies. Thank you, Hala. Okay, so now I can go back and explain how we exactly did this for our project. So to be able to decide whether an image is a food exposure image or not, we built a data set that consists of around 1 million images that were automatically collected from the web, particularly using two search engines, Google and Bing. And those images were divided into two classes. Images that have something to do with food, such as food items, advertisements, restaurants, and so on. And then the non-food images, which are typical things children would see on their daily trajectory, like animals, plants, locations, and objects. And to be able to do this, we usually use the search engine to issue queries and then retrieve the images returned for these queries. And these queries were really chosen so that they reflect our context. So things that, food items and advertisements and restaurants in Tunisia and Lebanon. And we crawled this through looking at food recommender systems like Yelp and so on. And then for the other class, we used, again, similar things that we expect to see in those two countries. And then since we were using web crawling and we know what queries generated which images, then the data was already labeled as food images and non-food images. And so we could directly take it and train a machine learning model. And again, if you remember, we have to split this data set into training and validation. And the convention is to split into 80% training and 20% test. And we trained a machine learning model on the training subset of this data set and then evaluated on the test data. And as you can see, our results, so we achieved a test accuracy of around 92%, which means that the model that we trained was not successful only 8% of the times in differentiating between a food image and non-food image. Next, please. Okay, and now here I'm actually showing you some statistics about our user studies. So once we've built that tool and trained the machine learning model, we actually deployed it in a real user study in Tunisia in 2020. And data was collected from 265 children aged 11 and 12 years in 29 schools. So that's part of our study, this data and this results. I mean, the study was slightly bigger. And in total, we managed to collect over 30,000 food exposure images, meaning those are the ones that were retained after the machine learning model was applied on the data captured by the wearable cameras. And if you look at the distribution here, which indicates the usability of the tool, so we see like sort of a normal distribution where there are few participants that did not have any footage recorded. So they returned with empty cameras, meaning that they opted out of the study or did not turn on the cameras at all. And then on the other extreme, we see people that had really big footage, so ranging from 12 to 21 hours of recordings. The next, please. These are some sample results from our user study in Tunisia. And you can see that our model was really successful in capturing a lot of food exposure images, and not just things that have to do with food items, but also if you look closely, we have images that have advertisements, images that have outlets. And as you can see in all of these images, faces were automatically blurred as our protocol promised through off-the-shelf tools such as MT, CNN, and CBLIP, which are image processing tools. Next, please. Now, once we've been able to capture data through wearable cameras and only retain the ones that have something to do with food exposure, we went a step further and actually also decided to even classify these images, food exposure images, into subcategories. So differentiate between the images that have food outlets, the ones that have food advertisements, and the ones that have food consumption, meaning that the child wearing the camera is eating something in that image or is exposed to other people eating something in an image. And of course, all of these could be, overlapping, in a sense an image could have an outlet and advertisement at the same time. Next, please. To be able to do this further categorization, we had to train another machine learning model. And in that case, we couldn't rely on the web because this was a very specific task, and it would be very difficult to just automatically try to get sample images from these subcategories. So what we did is we actually took a small part of our data that we collected in our user study, and we uploaded them on a platform called Labelbox, which is a crowdsourcing platform. This platform allows all sorts of annotation tasks through freelance workers. And in our case, these were images, and we wanted to label them or annotate them into these different classes, advertisements, outlets, or food consumption. And typically you give those annotators very clear instructions of what you want to do and how to annotate, in our case, an image. In addition to that, since we realized in our data and that the majority of the data were really fall under the category of food consumption, so we had to augment this data to include more advertisements or images of advertisements and outlets. And we used a public data set, which is egocentric food data set. And in addition, we crawled some images of food ads. And finally, we also included some images that were collected by data collectors in our study, which we refer to as the active data capture mode, which Christelle will talk about in a bit. Again, the data was split in the standard form, 80% training and 20% test. And we trained the machine learning model. And as you can see, the results of the model were significantly high. So it had a 96% F1 score, which really says that the model was very successful in differentiating between these different categories. Next slide, please. Finally, I'm going to talk about one additional model that we've built. And that model really focused on the children and what they're eating, and it tries to assess how healthy the food they consume is. So particularly given an image that represents food consumption, personal food consumption, meaning specifically for the child, this model would first extract the food items from that image because it contains multiple food items, and then it will use the ANOVA classification model to assess the healthiness of each food items. Next slide. So for example, if you look at the image on the left, this is one of the images from our user study in Tunisia, and you could see that it has actually 4 food items: the salad, the fried fish, the spaghetti, and the loaf of bread. And the food item detection model, its job was to basically extract each one of these food items. And then once we extract these food items, we apply or we subject them to another machine learning model, the ANOVA classification model, which is going to classify each one of these food items according to the ANOVA food groups. And why we chose the ANOVA classification system is because there is a lot of evidence that it has an impact on an impact on health, particularly for ultra-processed food. Next, please. So now I'm going to talk about how did we build or generate the training data for this last model, the healthiness assessment model. So again, we resorted to Labelbox, and we uploaded the 1,800 images that represent personal food consumption from our user study. And then, of course, we couldn't rely on the freelance workers to label this data because this requires nutritional expertise, particularly local nutritional expertise. So people who would be able to identify brands and ingredients of food items and are able to say, which NOVA group they belong to. And so we hired 4 Tunisian nutritionists on label box, and the job was to really draw a bounding box on every food item, as you see in the image, and then assign it to one or more NOVA groups. Okay, next, please. And just to try to illustrate how this works, I would ask you to go again on Menti or scan the barcode, and then maybe try to figure out how many food items are in this image. If you can't scan the barcode, I think you have to enter the code 1793 2526 once you get on Menti.
2525.
Sorry, okay, 256. Yeah. Okay. Okay, maybe I'll give 30 seconds more for more participants, but I see some consensus already. Okay, so we see that the majority. Okay, thank you. Yeah, so I see that the winner here is 6 food items. I see some people who said 7, some people who said 5. So it's really not a very easy task, even for this, just to figure out how many food items in there. But we typically, when we're doing these things and to give guidelines to the annotators, we have to try to make them think a little bit like a machine. So if you look at this, there are really 6 food items. So there's the salad, there is the main dish, there is 3 pieces of bread, and each one is in a different place. So those would be considered different food items. And then there is the orange. And if you look at the main plate, it had 2 pieces of bread as well, but that would be very difficult for a machine learning model to detect. So we had to really figure out what the machine can do, and based on that, decide how the annotation would work. So thank you for participating, and this is interesting. Okay, now again, the next question is, once we've identified a food item, let's say the salad in this case, typically the annotators would have to decide which NOVA group they belong to. So if you can, again, go in Menti and try to classify this, that would be great. Okay. Okay, great. So I see, a tie between group 1 and group 2, and then there is somebody who thinks it's a group 3. And again, this is not a very easy task, even for experts like you. It's really hard. I mean, you need to know what the ingredients are, and so in our case, our nutritionist labeled this as belonging to both NOVA groups 1 and 2. Group 1 because it's a salad, so it's considered, minimally processed food or unprocessed. And then because of the dressing, which is an oil, then that also belongs to group 2. But in practice, really, this is not a very straightforward task, and it's going to be even more difficult for a machine to perform. All right, thank you for participating. Now, our data set, once it was annotated on label box by our expert nutritionist, we ended up with over 4,000 different food items in the 1,800 personal food consumption images. And as you can see on top, these are the NOVA groups assigned to them. So the first column was NOVA group 1. The second column, for instance, is NOVA group 1 and 2, and so on. Okay. Then we again split the data into training and validation, and trained one model for food item detection to basically draw a bounding box on the different food items in an image, and another for classifying a food item into one of the NOVA classes. And as you can see, the food item detection model performed relatively well, so was able to recall or detect correctly 91% of all the food items in the test data. and had only 87% precision, meaning that it detected some things that were not actually food items. And when you look at the NOVA classification model, on average, it had an 86% F1 score, which means that was able to differentiate between these classes for food items, but wasn't as successful as the previous models, and that's because really this is the most difficult task that we had to do in our work. Right, and this is just a quick summary of the results from our user study for that last part or last component. So when we looked at our data, or the part of the data that I'm presenting here today, the 95% of the images belong to the food consumption category. And when we look on the right, there is a long tail distribution across the NOVA. Right, next. Okay, and these are some sample results, and you can see that the model was really successful in detecting all the food items in most of the images, even when an image has many of them, and was really doing pretty well, at least in this sample. Next, please. And this is the results of the model versus the actual true labels provided by the nutritionist for some sample, food items. So you could see, for instance, on the top image, the salad, the nutritionist labeled it as belonging to NOVA groups 1, 2, and 4 because it's a salad, it has cheese and some dressing, but our model wasn't able to detect that there was a dressing in this image. The second image, for instance, has a loaf, 2 pieces of bread or toast with some spread on it. Our model only detected that this belongs to NOVA group 3, where the nutritionists were able to, of course, to capture that there is some spread, which is chocolate, and that's, ultra-processed food. So in general, I mean, again, this task was the most difficult task, but we did have some reasonable results overall, right? Thank you. And now Christelle is going to talk about our second mode of data capture, which is active data capture. Thank you.
So thank you, Shadi. And I will be talking about indeed the second component of the study, which involved ground truthing or active data capture. Okay, so as mentioned at the beginning of this presentation, we use 2 different types of data captures to document children's food exposures on their daily trajectories. So the first one is basically involved the passive data capture using wearable cameras. It allowed us to generate a data set of images on children's food exposures, including the built food environment. And the images basically captured food exposure on children's daily trajectory to and from schools. However, the reality was that less than 10% of these images were about the built food environment. Also, we used a second method, which was an active data capture method using ground truthing, which I will be describing in the next slides. This method allowed us to generate a data set of images exclusively on built food environments around schools. So the objective of this component was basically, of course, to assess the quality of the school neighborhood food environment, but also we used it as a training data set for the machine learning model. If we can move to the next one. So I'm just going to give you a quick overview of the second component of the study. So the main objective, as we just mentioned, was to assess the quality of the built food environment in school neighborhood. We assessed availability, which was operationalized as count per area of the different types of food retailers and outdoor food advertisements available within a certain neighborhood unit or buffer zone. Here, just to mention that throughout this presentation, when we're using the word food, it also includes drinks and beverages. Now, for the neighborhood unit or the buffer zone, we opted for an 800-meter road network buffer around school, which corresponds to, we opted for this for an 800-meter road network because it corresponds to a 10-minute walking distance for an average school child, which is a reasonable walking duration. Now, it is important to mention that comprehensive street and road network data are mostly unavailable in most low and middle income countries, including Tunisia and Lebanon. And this is why the research team member, they they used a governmental open source map at the base map. Then they started to manually draw street level roads on ArcGIS. So this is a map showing in the middle the school in red with the buffer zone, and within the buffer, inside the buffer, you can see the road that were manually sketched by the research team. Now, for the fieldwork protocol, we conducted or we performed the ground truthing. So what do we mean by ground truthing? It means an in-person mapping with direct observation. So we basically ask data collector to walk within the buffer on the road, so within the buffer zone. They were given mobile phone, and we asked them to directly collect geographic coordinates and, of course, pictures of each food retailers and advertisement available within the buffer zone. And this was using an application called FERN2023, and this is a screenshot of this application. Next, we asked data collector to label the images by assigning a typology for each food exposure available within the buffer. And we followed a two-stage approach to label food exposures. First, we asked data collector to classify food exposure as food retailers or food advertisement, and this was the first layer of labeling. Then we asked data collector to further classify retailers by type using a context-specific checklist, which I will be talking about in the next slide. So for example, retailers were classified as kiosk or mobile vendors or traditional corner shops. In parallel, we also asked data collectors to further classify food advertisement by the type of food items promoted within the advertisement. So for example, if the advertisement included carbonated beverages or fresh fruit and vegetables. And this was the second layer of labeling. Now, when I talked about this context-specific checklist, it's important to mention that due to the lack of cross-context equivalence regarding the construct of food retailers, we designed a checklist that was adapted to the Tunisian foodscape after extensive discussion with experts from the country. And this is an example of this checklist, which included 13 categories. Now, as I mentioned, we used, so the data set that was generated from this ground truthing was used to assess, of course, the quality of the school neighborhood food environment. But we also used it to train the machine, the food exposure model. So so if you can see the second food exposure model that Shadi was talking about, was built to classify food-related images into food outlet, food consumption, and food advertisement. However, as he mentioned, we couldn't really collect enough pictures from the built food environment using the wearable camera. We didn't have enough pictures from the built food environment. This is why we used the data generated from this ground truthing to train the food exposure model. And of course, also the advantage that it is important to include images that are basically from the local food context, from the local foodscape. Now, for this particular for this particular food exposure model, we used the data set that had the first layer of labeling, so basically retailers or outlet versus advertisement. However, theoretically, we could have used the data set with the second layer of labeling, so the more detailed typology, to build a food exposure model that would automatically classify food-related images into the more detailed typology. So just to a bit summarize this component and think about implication for future studies. So the first step, we conducted the ground truthing to generate an image data set of food retailers and food advertisement that reflect the local context. Plus, we labeled these images by typology. Then this data set, basically we used it as a training data set for the machine learning model to build a food exposure model that was context specific to Tunisia in this case, because it included images that were specific to the local Tunisian foodscape. Now, if you think about that, this basically a food exposure model is a tool that could be used for future study. It's a tool that can be run on any image data set to classify food-related image into different categories, whether this image data set is collected from passive techniques or methods such as wearable camera, or active methods such as ground truthing. And here, just to mention that even in the future, we could conduct ground truthing methods to collect information on, for example, the built food environment, what we don't need anymore to label manually, because we can basically apply the machine learning model on the data set. And now moving back to Hala.
Thank you so much, Christelle. So in our last few minutes, we just wanted to share with you some reflections and lessons learned and things that we think need to be considered in studies that aim to do similar work to this in the African context, and then open it up for a discussion. So if you are considering using image capture to study food environments, it's likely that you will need to collect primary data in many of the African contexts, as secondary data are unlikely to be available in many of our contexts. In this case, it'll be important to think about whether this will be conducted through passive or active means, as Shadi and Christelle described these two methods. Active data capture would allow for better definition of things like time and space boundaries of food environments of interest, whereas passive methods give a better picture of actual lived experience of food exposures within environments. And these are some of the things that need to be weighed when making some of these decisions. You would also need to consider aspects of technology use, and we would recommend using or conducting user-centered design studies to help to develop culturally acceptable protocols that are relevant to your context, and really need to think through the ethical considerations of the research, as a lot of research related to images will have concerns around privacy of data. And that will always be part of the aspects that limit potentially some of the data. So for example, in our context, we had issues around safety and acceptability in certain neighborhoods in Lebanon, for example. It was impossible to obtain municipal permission to take pictures on streets. And we know from children, having done some qualitative research with them after the fact, that they turn their cameras off at certain points in time on the roads for sort of security concerns. So these are things to keep in mind anytime we're thinking about image capture to try to get an idea of food environments. And then consider whether that matters. So is it important to describe, so whether it matters if you have some missing data. So is it important for you to describe qualitatively these environments or to quantify these exposures in your research questions? So if your objectives are quantitative, then you need to think about what your denominators are in terms of time. So is it exposures over a 24-hour period, and space? So what is the definition of the space within which you're defining your food environments? And then this will have implications also on how you can, we didn't really discuss this, but we actually deduplicated images from the wearable cameras because we were collecting video footage, which had often, so if a person sat in front of the same meal for a long time, then you would have many images of the same meal. And so, but this could also be used to capture time spent exposed to a certain environment. So it's really important to try to define what it is you're trying to do quantitatively in terms of time and space in a lot of this work. The other key issue that is really that for this type of research, you need a very strong contextual understanding to inform the machine learning approach. So some of the questions you would need to consider is, where are food exposures likely to occur in your context? And then what are the types of food exposures? For example, the different types of outlets, formal and informal, within this environment that you may want to capture. And then, as you saw with the labeling of anything that is related to food in many of these contexts, food takes on very different visual aspects and cultural aspects in different contexts. And so really having local nutritionists to label food-related images and to help train these data sets will be extremely important. And then, as you saw, classifying mixed foods and foods that don't necessarily have labels on them or brands is quite complex. And then just thinking through what data on the geographical scope of your environment exist, and will you need to define the geographical boundaries or need to generate these geographical boundaries of your food environments as you're thinking about conducting this work in these contexts. And then moving forward, when thinking about using these kinds of methods in the African context, it will be really important, therefore, to have very well-defined research questions. You know, are you interested in food consumption or built food environment? Are you interested in quantifying these environments versus describing them qualitatively? What are the classifications? So we used NOVA to guide our typologies. We used a context-specific checklist to guide the typology of outlets. So what are the outcomes of interest in terms of classifying that you want these machine learning models to help you with? And then just to add that you can actually think about how these data will complement other components of research, and they may aim to link, for example, food environments to health outcomes. So in our case, we combine some of these data with survey data on children's nutritional status, and so it sort of helps to complement other research methods rather than a standalone method. And the other sort of thing we found extremely important was the need for an interdisciplinary team. So although we as nutritionists or food system and public health people can learn machine learning methods, having expertise on the team was really important for us, and ensuring that the applied work we're doing is also relevant for their discipline. So when you are doing interdisciplinary work, the ability of Shadi to publish in computer science journals was extremely important, or an incentive really for this kind of interdisciplinary work. So moving forward, you know, clearly this is a rapidly developing field with many opportunities to think about big data repositories and data sharing, whereby more application, you know, the more applications we have for these types of data, the more intelligent our machine learning models will become, helping us to automate more of these kinds of tasks that will help us to better understand our food environment and to inform interventions to make them healthier. So just before opening the floor up for questions, it would be great to hear from you through our last Menti, what you think the challenges of adapting similar methods in your context might be. And then we'd love to have, I think we have about 10 minutes for questions after that. So any thoughts or reflections in the Menti, but also if you want to put your hands up, we're happy to take questions. Thank you.